Lesson 42, the chi-squared goodness of fit test. The chi-squared goodness of fit test is a versatile inferential statistics method used in the analysis of categorical data. Specifically, the chi-squared goodness of fit test is a hypothesis testing procedure used to determine if the expected frequencies for the categories of a qualitative variable reasonably match or fit the observed frequencies for these categories in a sample. The expected frequencies are generated according to the particular hypothesis under investigation. These expected frequencies are based on the predicted proportions of each category according to the hypothesis being tested. The observed frequencies are determined by the actual sample data values. So essentially, a chi-squared goodness of fit test allows us to predict the percentages of certain categories and then test to see if these predictions accurately reflect what is observed in the sample data. So this chart here provides us with an outline to follow to take us through the steps of our chi-squared goodness of fit test. The chi-squared goodness of fit test begins with the formation of a hypothesis, which is used to generate the expected frequencies. The stated hypotheses, HO and H1, are always expressed in the same manner. That is, HO is always that all of the expected frequencies fit the observed frequencies, and H1 is always that not all of the expected frequencies fit the observed frequencies. Now, unless there exists a compelling reason to do so otherwise, hypothesis testing procedures are conducted using the customary 5% level of significance, that is, an alpha equal to 0.05. Now, to calculate the p-value needed to make the decision, we could use the TI-84 calculator. To do this, we have to enter the observed frequencies, or sample data, into list 1, and then we need to enter the expected frequencies into list 2. So the two lists of data that are entered into the calculator are the observed frequencies and the expected frequencies. The observed frequencies are the actual data values. That is, when we have a qualitative variable that has C categories, O1, the first observed frequency, is the number of data values that fit category 1. O2 would be the count or the frequency of data values that fit category 2. And finally, O sub C would be the frequency or the count of the data values that were observed to fit category C. The expected frequencies are generated according to the idea in the hypothesis. This idea is generated by predicting the certain percentages, P1, P2 through PC, of the corresponding categories in the variable. So here we predict that a certain P1 percentage of the data would fit category 1. And we predict that P2 certain percentage of the data will fit category 2. All the way through PC percentage of the data is predicted to fit category C. To turn the percentages into the expected frequencies, we multiply the proportion by the corresponding N sample size. N, the total sample size, is found by taking the sum of all the observed frequencies, the O1 plus O2 and so on plus OC equals N, the total sample size. Taking this N sample size times the hypothesized proportions for each category generates the expected frequencies used in the chi-squared goodness of fit test. After the observed frequencies are entered into list 1 and the expected frequencies are entered into list 2, the chi-squared GOF test command on the TI-84 calculator will calculate the desired p-value for the hypothesis test procedure. This is done by pressing Stat and Enter to get to the list editor. Here we will enter the observed values in list 1 and the expected values in list 2. The chi-squared GOF test command is found by pressing Stat, arrowing over to Tests, and then arrow up until the cursor is next to chi-squared GOF test. GOF, short for goodness of fit. Press Enter. Next to the observed, we enter in the list where we entered the observed values, in this case list 1. Next to expected, we enter in the list where we entered the expected values, which was list 2. The degrees of freedom in a chi-squared goodness of fit test is C, the number of categories of the qualitative variable, minus 1. So if we have 4 categories, minus 1 leaves us with 3 degrees of freedom. Press enter under calculate, and we get the desired result, that is, the p-value. The p-value that the calculator gives us is then used to reach the decision in the hypothesis test procedure. The formula that is programmed into the TI-84 calculator for the chi-square test is given here. This test statistic for this hypothesis test procedure is denoted by what looks like the letter x being squared, which is really the Greek letter chi being squared. Thus, the symbol used to denote the formula, the Greek letter chi squared, gives rise to the name chi-squared goodness of fit test. Now, the formula involves taking the observed values and subtracting the expected values. When we take the observed values minus the expected values, we're finding how different the predicted or expected values were from what actually occurred in the sample. Now, if we make an overestimate on the expected value or an underestimate on the expected value, the resulting differences will either be negative or positive. Thus, if we were to find the total of all the differences between the observed and expected values, the negative numbers would cancel the positive numbers, leaving us with 0. That's why the squared is introduced in the formula. The observed minus the expected value squared makes those differences positive. Thus, when we add them, there's no cancellation occurring. Now, when the expected frequencies fit the observed frequencies, the O value and the E value are close together. Thus, the chi-squared test statistic will be relatively small or close to 0, because the observed value minus expected value, when they're close, will be a small difference. This will produce larger p-values, thus giving rise to support that HO, that all the expected frequencies fit the observed frequencies, is a valid idea. In order for the chi-squared goodness of fit test to be applied, the independent random sample must be sufficiently large. This can be accomplished by ensuring that the sample size is large enough so that all, or nearly all, of the expected frequencies are 5 or more. Also, none of the expected frequencies should equal 0. In that case, the chi-squared test statistic would be undefined. The calculated p-value is used to reach the decision regarding the validity of HO. Small p-values provide sample evidence contradicting HO. That's why when the p-value is less than or equal to alpha, we reject HO. And large p-values provide sample evidence consistent with HO. That's why when the p-value is greater than alpha, we do not reject HO. When HO is not rejected, the conclusion is that all of the expected frequencies fit the observed frequencies. Thus, the hypothesis used to generate the expected frequencies is valid. When HO is rejected, the conclusion is that not all the expected frequencies fit the observed frequencies. Hence, the hypothesis used to generate the expected frequencies is not valid. So now that we've learned the chi-squared goodness of fit test, let's try some examples to help demonstrate its use.